Climate change is one of the main factors or drivers in the dynamic baseline, along with economic growth and demographic changes. Water and sanitation policy interventions will occur in a world with increasing temperature, sea level rise, and more extreme weather events. For water, sanitation and hygiene sector professionals, it's important to consider the question of whether WASH investments will be more or less effective or economically attractive in a world with a changing climate. The consequences of climate change for the water supply and sanitation sector are complex and multifaceted, and, a priori, the answer to this question is not clear. In this video and the next, we're going to look at the effects of climate change from two perspectives. First, in this video, we'll look at the effects of climate change, health and water from the perspective of the household. In the next video, we'll look at the effects of climate change from the perspective of a water utility. Two of the principal economic benefits from water and sanitation investments are the reductions in mortality and morbidity risks compared to baseline conditions. But these baseline conditions are evolving due to climate change. How climate change will affect these baseline health conditions is still uncertain. The question of how climate change will affect public health is a huge and complex topic, one which we cannot explore in depth in this MOOC. But, as current and future professionals in the WASH sector, we do want to encourage you to think carefully about climate change and health from both the household and the utility perspective. We especially want you to reflect on how challenging it is to predict how households will respond or adapt to the increased risks to their health, and what this means for the economic evaluation and selection of water and sanitation investments. This figure shows 8 pathways through which climate change may affect a household's health and well-being. The size of the arrows here suggests some preliminary estimates of the size or importance of these pathways, but these are highly uncertain and likely to change from one location to another. Note that most of these 8 pathways involve water. If you look at the problem from a poor household's perspective, you can see how difficult it is to adapt to so many increased health risks. There are so many pathways, the effects are uncertain, and the payoff from adaptation measures is uncertain. Water and foodborne infections may increase due to higher temperatures, increasing the chances of household members getting sick. This is especially a problem for poor households who lack refrigeration. Increased temperatures and changing rainfall patterns may expand the range of vector-borne diseases such as malaria and dengue. These risks may increase if more irrigation is needed to adapt to erratic or less rainfall. If increased temperatures and more erratic rainfall decrease crop yields, this may decrease the food supply of poor subsistence households, leading to reduced health. Increased temperatures will lead to increased crop water requirements. Irrigation may be an important adaptation measure, but a household will need money for this. Increased temperatures may directly affect health through heat stroke. Increased temperatures and increasing health risks will hit some occupations, such as those that require outdoor labour, especially hard. For example, for farmers and unskilled labourers, working outside during the heat of the day is going to become increasingly difficult as temperatures rise. Drinking and cooling water requirements for labourers will increase, and productivity will fall. Wages may adjust downward. There is increasing evidence too that rising temperatures increase violence and civil conflict. These effects are added to the stresses associated with floods and droughts. A household may move or try to protect themselves from crime. Note that to the extent that climate change contributes to migration, this may be a reason not to increase in investments in water and sanitation infrastructure in locations that are left behind. Extreme weather events such as typhoons and droughts directly threaten the lives of household members. The risk of fires will increase in many areas. Households have multiple ways to adapt to extreme events, including the purchase of insurance, moving to better locations, and increasing liquidity to deal with emergencies. Another important link between climate change and health is through air pollution, and higher temperatures exacerbate air pollution, particularly ozone and fine particulate matter, which has a large adverse effect on health, including respiratory disease associated with ozone and cardiopulmonary disease, and lung cancer associated with particulate matter. This next slide shows that the size of the effects from these different pathways will increase by 2030 to 2040 if no adaptation measures are taken. This is based on estimates by the IPCC Working Group 2 on health, from both the literature and from expert judgment. Water and sanitation investments are one adaptation method that can address some of these adverse effects. For example, piped water services may enable a household to irrigate a home garden to reduce the effects of malnutrition. Improved household sanitation will likely become more important as food contamination increases due to higher temperatures. But there are other climate change and public health pathways that WASH investments can do little to ameliorate. This next slide shows that the magnitude of these health effects are likely to increase over time if mitigation and adaptation measures are not adopted. As shown, after the malnutrition pathway, the direct adverse effects of increased temperatures on health are increasingly important. Access to piped water supplies can help household members keep cool through increased opportunities for baths and showers. Bringing water sources outside the home closer to dwellings will reduce collection times and the exertion of household members, especially during periods of high heat. But piped water in the home will likely become an increasingly important priority to households as temperatures rise. In this slide, the arrows show how the size of the effects may increase from the present state, shown in yellow, to that of 2030 to 2040, shown in orange, and to 2080 to 2100, shown here in red. This slide shows the magnitude of the effects through the different pathways without additional adaptation, shown in red, and how these can be reduced with a high level of adaptation, shown here in blue. But all these calculations are highly uncertain. They are really just educated guesses. We now turn to one of the 8 pathways through which climate change can affect health, the food and waterborne infections pathway. WASH professionals are especially concerned about how climate change may affect waterborne diseases. What do we know about how increased temperatures and increased precipitation affect the incidence of diarrhea? Well, it turns out that this is not an easy question to answer, nor, as we have emphasized, is it likely to be the pathway of greatest concern to the household. One reason that this is not an easy question to answer is that diarrhea is caused by multiple pathogens. These different pathogens will respond in different ways to increases in temperature and precipitation. For example, diarrhea caused by bacteria and protozoa tend to peak in wet and warmer seasons, while viral diarrhea cases tend to peak in cold and dry seasons. Also, the relative importance of different pathogens will vary from one location to another. Diarrheal incidence often has distinct seasonal patterns. This slide shows seasonality in the pattern of hospital admissions of Peruvian children for all-cause diarrhea. As shown, admissions tend to increase when temperatures increase and humidity decreases. This is an arid setting where rainfall is low all year round. But in other settings, rainfall has been significantly associated with diarrheal disease. Thus, to the extent that climate change affects seasonal temperature, rainfall, and humidity patterns, diarrheal incidence may be affected. This next slide shows seasonal patterns in norovirus cases in China and Germany. The vertical axis shows the proportion of cases normalized by location over all years for each study, presented by month. The pattern is most pronounced in Germany, where norovirus cases increase and peak in the winter when temperatures fall. This is the opposite seasonal pattern from diarrheal cases in Peru, where it is likely that bacterial and/or protozoal pathogens dominate. Warm temperatures might thus decrease the number of norovirus cases or affect the relative dominance of different pathogens in a location at different seasons. These patterns illustrate the spatial heterogeneity of diarrheal seasonality, where local weather patterns, geography, and other factors affect diarrheal incidence over time. This slide presents a third example of seasonality and waterborne disease incidence, this time for cholera. The figure on the left shows monthly cholera deaths in Dhaka between 1893 and 1940 from historical records for India. The typical seasonal pattern exhibits 2 peaks a year and is modulated by longer cycles with considerable variation in total deaths from year to year. The figure on the right shows average monthly changes in cholera cases from Bengal and Madras, which have 2 peaks per year. Both regions have high annual rainfall. The shift shown in the bimodal seasonal cycles in Bengal and Madras depends on the seasonal timing of the southwest monsoon in Bengal and the northeast monsoon in Madras. Also shown is the Punjab, which has drier climate and a single cholera peak per year. Again, these data show distinct patterns in disease incidence and weather, suggesting that climate change is likely to affect the timing and patterns of disease in complex ways. This final slide summarizes the results from several studies that have investigated the relationship between mean ambient temperature in degrees Celsius and diarrheal disease. The figure shows the estimated percent increase in relative risk of diarrheal cases, often this is hospital admissions, incidence or Z-scores associated with each 1 degree Celsius increase in mean ambient temperature. Single empirical studies are shown in black. Meta-analyses summarizing multiple studies are underlined in blue. These studies use different models, time steps, and control for different covariates, so they should be compared with caution. The 6 studies summarized in the top half of the figure use all-cause diarrhea or infectious gastroenteritis for their outcomes. The 3 studies in the bottom half report results for rotavirus. Since the 6 studies summarized in the top half are not pathogen-specific, the causes for diarrhea may include protozoa, for example Giardia, Cryptosporidium, or bacteria, for example E. coli or Campylobacter, or viruses, for example rotavirus and norovirus. The results for all-cause diarrhea suggest a 3 to 11% increase in cases with each 1 degree Celsius increase in mean temperature. However, one meta-analysis by Lloyd and co-authors from 2007 did not find a significant relationship between temperature and diarrheal disease. However, this study used large annual or multi-annual study length, time steps instead of shorter weekly or monthly time steps like the individual studies, and found rainfall to be significant. 2 of the rotavirus studies, both Jagai et al. And Levy et al., found a negative correlation between temperature and rotavirus. This corroborates the general findings that rotavirus cases increase in colder months, likely because of greater time spent indoors, with the hypothesis being that part of the transmission is through inhalation or air. Rotavirus seasonality is similar to norovirus seasonality that we observed in prior slides. However, one study by Hashizume et al. In 2008 reports nonlinear threshold effects for rotavirus at high temperatures. They found that above 29 degrees Celsius there is a 40% increase in rotavirus cases with each additional 1 degree Celsius increase in temperature. Because bacteria and protozoa incidence increases in warmer temperatures, all-cause diarrhea results are biased towards the null hypothesis, of no effect when there are multiple pathogens contributing to the outcome. The bottom line here is that there is a lot of variability in the results and lots of different factors at play. A key message from this video is that understanding households' budget priorities and their demand for improved water and sanitation services in a world of climate change will become increasingly challenging. Water and sanitation investments are likely to be an important adaptation measure in many circumstances. But this cannot simply be assumed because households will have so many adaptation needs, and priorities will be different in different locations. There is still a great deal of uncertainty about the effects of climate change on waterborne diseases. Higher temperatures are likely to increase diarrhea cases modestly, but there is likely to be a great deal of spatial and temporal heterogeneity in the effects of climate change on waterborne diseases. Some effects from the various pathways discussed in this video can be dealt with at the household level, but others must be addressed by the state. But all the adaptation measures, whether paid for by the household or by the state, require money. Thanks for watching this video.